Okay, so in this video we're just going to review the practical quiz that we did on the AC loudspeaker. So let's get started with that. Okay, so first of all, clue is in the name. We need an AC power source for a loudspeaker because we need the electromagnet to be constantly changing direction. So in the UK, as I said in the video, our electricity goes through cycles 50 times every second. So essentially we're getting one whole wave every 0.02 seconds. So that's why we get 50 every second. Okay, so which of these statements best describes the magnetic field around the coil during phase B of the alternating current? So phase A is when the current is positive, phase B is when the current is negative, essentially. So let's hop into OneNote where I want to go into a little bit more detail on this. So general things about magnetic field, electromagnets. So the bigger the current is, the magnetic field strength will increase. Okay, that's a good general rule to know. And if current changes direction, the magnetic field changes direction as well. So in B, if I just draw a field, so here's our coil. It has a soft iron core in it. So now what's happened is our current is now going this way. So our current is now going the opposite way around. And what that means is the North Pole is now over here and the South Pole is over here. So if we look at the graph, the values of current that B goes through are the same as it goes through for A, but they're negative instead of positive. So we haven't changed the strength of the field at any point. But what we have done is we've reversed the current. So that means the magnetic field around the coil is now in the opposite direction. So if we flip back into this one, so the one we want is the magnetic field direction is reversed, but it's the same strength at different points. So although the magnetic field strength is definitely varying as we go through cycle B, it goes through the same variations as it does going through A. Okay, so looking at doing some explaining again. So explain why the permanent magnet jumps up and down, colliding with the loudspeaker cone. So again, I want to put some detail into this. So I think there are two key phases to look at. So we're still going to be using our phase A and B. Now, the direction of these forces were somewhat arbitrary, so we could have reversed the whole thing. So during A, it could have been a force downwards, and during a B, it could be a force upwards. That doesn't matter too much. So I just said during phase A, the force is upwards, and during B, it's downwards. So anyway, starting our explanation. So when there is a current, just like with our DC Bell explanation, if there is a current in your electromagnet, there is a magnetic field produced around the coil. That's the first key thing. So that actually brings up a point here. So there are 3 points during the cycle where there is no magnetic field, and I'll mark those 3 with these blue blobs. So if there's no current, there is actually no field, but most of the time there is a field. So the reason we get a magnetic force or a Lorentz force is because we have 2 magnetic fields that interact with each other. So the magnetic field from the electromagnet and the magnetic field from the permanent magnet interact, and that produces a magnetic force. So that's the key. To get a magnetic force, we need 2 fields that interact. During phase A, the current is in a direction such the magnetic force is produced, I need to add a D in there, is produced upwards, which is greater than the magnet's weight force, so it accelerates upwards. And the detail I should add in there, so the resultant force is upwards. And that's why it accelerates upwards, because the resultant force is upwards. During phase B, the current is reversed, so the magnetic field around the coil is now in the opposite direction. And that's why the magnetic force changes direction. So the magnetic force is now in the opposite direction, and the magnet accelerates downwards as the resultant force is now downwards there. And some people put in, which I really liked, is they were saying that that as the magnet strikes the cone, it causes it to vibrate, which in turn vibrates air molecules, producing a sound wave. I thought that was a really nice addition some people put in, so I thought I'd flag that up as well. So that would be our explanation about why the permanent magnet jumps up and down, colliding with a loudspeaker, we're talking about the direction of the resultant force during phase A and B, and the fact that it's in the opposite direction with each of those. And I think just like with the DC bell, I think it would be quite a good idea if we made a quick note of this explanation in your additional notes section of your booklets. So again, you've got this explanation written down. Okay, so final part we need to look at is we had a piece of foil with a current going through it inside a permanent magnetic field, and we need to predict which way it experiences a force. So I put this in here because it's a good chance to practice using our Fleming's left-hand rule, as that's always something it's good to work on. So first key thing to remember, something that causes people a few issues, is if you have current and magnetic fields that are perpendicular, that will produce a force that is perpendicular to both the field and the current. And what that means is the force can't possibly be to the right, it can't be to the left, because that would make the force parallel to the current. And the force can't be into the page or out of the page, because that would be parallel to the magnetic field. So that's always a useful check to make sure you've done it correctly. So essentially what that means is the force has to be either up or down, because those are the only directions which are perpendicular to both the current and the field. So we use Fleming's left-hand rule to decide which of those two it is. So you can see here, I've got the field going into the screen, if you like, because that's pointing from north to south. You've got the current is going from left to right, because you can see that marked on the diagram. So your thumb points upwards, so the force, the Lorentz or magnetic force, in this case, would be upwards there. Okay, so that finishes off our review of the AC loudspeaker practical quiz.